right, welcome back to second part of the gas laws notes, and now we're actually going to talk about the gas laws, which really just means some math equations. But don't let that freak you out, because in all honesty, these are very, very simple. So, 4 variables that we consider with gases. We talked a little bit about pressure, we've talked a little bit about volume, the space that they take up, we talked about temperature, and those are all represented by those P, V, and T letters. And then something else that we kind of have to think about, although in this lesson we're going to hold this number constant, is the number of moles present. And we represent number of moles in chemistry with a lowercase n. That is the traditional variable that represents number of moles. Also, it should be noted that there is this idea of something called standard temperature and pressure, abbreviated as STP. Anytime you see the words standard temperature and pressure or STP, that means that the conditions that that gas is in is 0 degrees Celsius for the temperature and 1 atmosphere for the pressure. So if a word problem is asking you to make a calculation and they talk about the gas is at STP, they're telling you what the temperature and pressure conditions are. So let's dive right in. The first gas law that we have to look at is this equation. It's called the combined gas law because it combines all 4 of those variables: pressure, volume, moles, and temperature. And these little subscripts, all they really mean, this looks really complex, but all these numbers mean is that if I'm reading a word problem and it tells me that a gas is at a certain pressure, a certain volume, a certain number of moles, and a certain temperature, and then we change some of those conditions. So let's say we heat it up. So T1 is describing what the temperature was originally. T2 would be describing what the new temperature is, or what the temperature is after we heat the gas up. Same thing for pressure. Let's say we have it in a container and we increase the pressure. So we take the pressure originally and then we change it to some new pressure. And then same thing with volume. It's a certain volume and we change the volume. So that's what these subscripts mean. So 1 is just representing initial conditions and 2 represents the final conditions, if you will. And I will tell you, excuse me, that moles is here in this calculation, but we're going to go ahead and hold moles constant, which means if I kind of move some things around in this equation, and let's say I move to this other side, mathematically to do that, I multiply into on both sides and it will cancel over here. So the n will go away, but if I multiply it on this side, I got to multiply it over here. So I'll end up with n up here on the top. Well, if n2 and n1 are the same number, they just go away. And that's what we're going to do. We're going to make that assumption is that everything in this lesson is holding moles constant. So essentially we're going to ignore this n and only look at P, V, and T. So combined gas law is where pressure, volume, and temperature are held constant. Let's take a look at an example. Okay, so in this example, it says we have a gas that is heated from 263 Kelvin to 298 Kelvin. So I can tell that there's a change in temperature. And I can label those if it helps. It says the volume is increased from 24 liters to 35 liters. So there's a change in volume by moving a large piston within a cylinder. If the original pressure, so talking about original pressure, is 1 atmosphere, that means P1, what would the final pressure be? That's talking about P2, assuming there's no change in the number of moles. So what I like to do is kind of make a list of all the variables that could possibly be going on here. So we had P1, V1, T1, there's also P2, V2, and T2. And just kind of plug them in to see what we're working with. So pressure, the original pressure was 1 atmosphere. The original volume was 24 liters. The original temperature was 263 Kelvin. The original pressure was, the final pressure, that's what we're solving for. So that's our unknown. Our final volume went to 35 liters and our final temperature was 298 Kelvin. And so what I notice is that in this particular example, we see a change in everything, every component with the exception of moles. So what that tells me is that I am using combined gas law. So P1V1 over T1 equals P2V2 over T2. And I leave the moles out because this says there's no change in the number of moles, which means I don't need to include them in my calculation. So I am simply going to just do a little bit of double checking here. As long as my volumes are in the same unit, I don't have to make a conversion. As long as my temperature is in Kelvin, that's what I have to use. And then I'm solving for pressure. So if pressure is starting in atmospheres, it's going to end in atmospheres. And then I'm just going to substitute into my equation. So P1 is 1 atmosphere. V1 is 24 liters. And all of that is divided by T1, which is 263 Kelvin. We set that equal to P2, which is our unknown. So you can write P2 or you can write X if that makes you happy. V2 is 35 liters and T2 is 298 Kelvin. We're going to solve for P2, so we need to isolate that variable. To do that, we'll multiply both sides by 298, canceling here, and then we'll divide both sides by 35, canceling there, leaving P2 by itself. Plug all that in the calculator. Make sure your calculator knows you want both of those things in the denominator, so be very careful about your PEMDAS rules. And then my calculator tells me that P2 is equal to 0.78, and we were solving in atmospheres. All right, so Boyle's law. Boyle's law is named for a guy, and his last name was Boyle. And he did some experimentation where he held temperature constant to see how pressure and volume were related with a gas. And so what I have here initially is the combined gas law where we've ignored that N. But again, that same explanation about how if we hold something constant on both sides, that means it's the same number on both sides, and what happens is mathematically those things cancel out. So if we cancel out temperature, because Boyle's law means constant temperature, we end up with P1V1 equals P2V2. So when you're reading a word problem, you just identify what is P1V1, what is P2V2, which one of those variables that are you solving for, and then you manipulate it algebraically. Let's try one. So here we have a question that says if 22.5 liters, so that is a volume, of nitrogen at 748 millimeters mercury, that is a pressure, and I know that because of the unit, are compressed to 725 millimeters mercury. That is another pressure, so here's my initial, here's my final pressure. At constant temperature, that's important, what is the new volume? So again, we'll make a list. P1, V1, T1, P2, V2, T2. And again, I'll say we're assuming for every single example, we're holding the number of moles constant so that we can ignore the N. But in this example, we're also holding temperature constant. So anytime you hold something constant, we just ignore it and get rid of it. So let's label what we know. My initial pressure is 748 millimeters mercury. My final pressure is 725. My starting volume is 22.5 liters, and the final volume is actually what I'm being asked to find. And again, it doesn't matter what unit of pressure you're in as long as they are the same. So if one of these is millimeters mercury, the other one has to be millimeters mercury. Same thing with the volume. If this starts in liters, that's what I'm going to be solving for in liters. So if I go back to my equation, if I'm holding temperature constant, I'm going to ignore that, and I end up with P1V1 equals P2V2. This is Boyle's law, the one that holds temperature constant. And then I just make substitutions. So P1 is 748. V1 is 22.5 liters. I set that equal to P2, which was 725. V2 is my unknown, and then I algebraically manipulate this to get V2 by itself, which means we're going to divide both sides by 725. And then I can plug this term in my calculator, and my calculator tells me that V2 is 23.2 liters. Very good. Okay, now we're to Charles' gas law. Charles' gas law holds pressure constant. So if we hold pressure constant, that means it just cancels out on both sides. So if we remove the pressure, we are left with V1 over T1 equals V2 over T2. And again, you just identify what variables you know, what you're trying to solve for, plug everything in, and then manipulate it algebraically. It is important to note that your temperature here must be in Kelvin. So if the word problem gives it to you in Celsius, you need to convert it to Kelvin. If you're doing a UT Quest problem that says answer in units of Celsius, you still need to convert your temperature to Kelvin to do the math, and then you can convert it back to Celsius to report your answer. In terms of the volume unit, it does not matter if the volume is reported in milliliters or liters or any other volume, as long as they are the same. Let's try an example. So here we say we have a gas that occupies 900 milliliters. So milliliters is a unit of volume at a temperature of 27 degrees Celsius. So that is a unit of temperature, of course, and constant pressure. What is the volume? So that's what we're solving for at 132 degrees Celsius. So again, let's make ourselves a list and identify what we know. P1, V1, T1. P2, V2, T2. This says constant pressure, which means we are going to ignore our pressure variable because we're not changing it. So our initial volume is 900 milliliters. It doesn't matter if that's in milliliters or liters as long as we're consistent across V1 and V2. V2 is actually what we're solving for, so that's our unknown. T1, the temperature at when this was at 900 milliliters is 27 degrees C, and T2 is 132 degrees Celsius. Our temperature must be in Kelvin for this to work. So to do that, we add 273 to both of these temperatures before we can plug them in. So by adding 273, this is 300 Kelvin, and this one is 405. Then we take a look at our equation. P1 V1 over T1 equals P2 V2 over T2. But of course, we've canceled the pressure variable, so we end up with just V1 over T1 equals V2 over T2. And now I plug my numbers in, substitute. So 900 milliliters for V1 over 300 Kelvin equals V2 is my unknown over 405 Kelvin. And then again, I algebraically manipulate this to get V2 by itself. To get 405 onto this other side, I'm going to multiply both sides by 405. Then plug this into your calculator and you find V2 equals 1,215. And since we were solving for volume and our original unit of volume was milliliters, that is what we find here. And the last one is Gay-Lussac's gas law. And he did his experimentation under constant volume. So we're going to cancel the V's and remove them. leaving us with just P1 and P1 over T1 equals P2 over T2. Again, the temperature must be in Kelvin to do the actual math. The pressures, it does not matter what unit of pressure you do the math in, as long as P1 and P2 are the same. So if you're doing a UT Quest problem and it says answer in units of atmospheres, but maybe the pressure given to you in the question is in mmHg, you can either do the math in mmHg and convert to atmospheres at the end, or you can convert to atmospheres first and then do the math. It does not matter, you're going to get the same answer. So that is Gay-Lussac's gas law, and we will try a quick example. Okay, so here we have 10 liters of oxygen gas originally at STP. And remember, STP does tell us numeric information about temperature and pressure because this is the definition of standard temperature and pressure. And this says it's held in a rigid container. Anytime you see this term rigid container, that's the same thing as saying constant volume. Because if the container can't change size, the volume is going to remain constant. It says this container is heated to 512 degrees Celsius. What will the new pressure be of this gas? So just like always, let's keep track of what we know and what we're trying to find and what's being held constant. So we said constant volume, that's Gay-Lussac's law, right? So if we're constant volume, we get rid of the V's. So now pressure, the original pressure, well, this told me it was at standard temperature and pressure, and standard pressure is 1 atmosphere. Standard temperature is 0 degrees Celsius. It says the container is heated to 512 degrees Celsius, so we're changing to 512 degrees Celsius, and we want to calculate the new pressure. So again, your pressure units don't matter as long as they're consistent. So if I'm starting in atmospheres, I'm going to end in atmospheres. Our temperature units do matter. We have to put this into Kelvin by adding 273. So we're starting at 273 Kelvin and we are ending at 785 Kelvin. And then I just plug it into my equation. So I'm going to ignore the V, which leaves me with just P1 over T1 equals P2 over T2. Make my substitutions based on what I know. P1 is 1. T1 is 273. P2 is unknown. And T2 is 785. This is the perfect example of one of the reasons why we have to convert temperature to Celsius, because I cannot put 0 as a denominator. So I had to convert this from Celsius to Kelvin because I can't have a 0 down here. I also don't want to have a negative number down here because you can't have, if I solved with a negative number, then I would end up with negative pressure, and that's not possible. So when I manipulate all of these variables, I'm just going to multiply by 785 on both sides. And my calculator tells me that this is 2.9 since I'm solving for pressure and my unit pressure here was atmospheres. Got to make sure I label that. Great work.